Hello everyone. In this video, I'm going to show you how to perform some of the routine formulations and calculations for robotics using MATLAB Symbolic. So, for example, let's say you want to calculate the Jacobian for this robot, right? And you want to use the differentiation method, not the DH method. So if you call this point end effector and show it with E, and if you just focus on the x and y motion of the end effector for Jacobian and not all of the potential degrees of freedom, some of them are zero, like z omega x and omega y, and then omega z, which is just not an independent degree of freedom. So you know this robot has 2 degrees of freedom. And so we just focus on x of e in base and y of e in base, right? We want to just focus on those. Then based on what we had in the past, x of end effector in base, it is like L1, correct? Times cosine of theta 1 plus L2 times cosine of 1 plus 2, and then y is L1 sine 1 plus L2 sine 1, 2. And if I want to relate the xi, correct, the end effector velocity, which in this case is simply v of end effector in base, the x component, and v of end effector in base, the y component, or basically the time derivatives of these two x and y, you know I can relate it to the angular velocities of the joints q1 dot and q2 dot using the Jacobian. So it's Jacobian of vector q times vector q dot, where this Jacobian of the robot, in this case, if you remember, in general, it is going to be partial of f1 with respect to q1, partial of f1 with respect to q2, and then similarly partial of f2 with respect to q1, and partial of f2 with respect to q2. And the question is, what is f1, what is f2? Those are these functions that you see here on the top. One of them is for x, the other one is for y. So this one is like f1 of q1 and q2, the function that you use for x. And here, this one is your f2 of q1 and q2, correct? So now, can I calculate these partial derivatives in Jacobian using MATLAB Symbolic? So I define my angles Q1 and Q2 using MATLAB Symbolic, and then I can calculate J, even I can calculate Xi as a function of Q and Q dot. If I also define Q dot symbolic, can I basically calculate it? The answer is sure. How do you do that? Well, here we go and define our parameters using the symbolic command syms. Syms define those parameters as symbolic. So we say, hey, syms of q1 and q2, and then we define a1 and a2 or l1 and l2. It all depends on what you want to do. So if I want to not go through the big code that I wrote for all dynamics calculation, if I just want to focus on Jacobian, then I say syms of a1 and a2. Or if I want, even I can define the length of the members as symbolic too. So I can say, hey, L1, L2, and then Q1 and Q2, correct? So I define them as symbolic. And now all I need is to define functions f1 and f2. So f1 is like L1 times cosine of Q1 plus L2 times cosine of Q1 plus Q2. And then similarly, I have the function f2. So this is just going to be sine. right? And now if I want to calculate Jacobian, I say Jacobian is what? In MATLAB, the command diff, if you watch my video on MATLAB Symbolic, the command diff does symbolic differentiation. And so here I say partial of f1, but since it's partial, I define the variable, so it's with respect to q1. And the variable with respect to which you are going to take derivative, you definitely need to put it in a single quotation. And if the order of the derivative is more than one, let's say second derivative of f1 with respect to q1, then you can provide the order as well here. If it's just first derivative, you can either say 1 or you don't need to specify it, because the default, if you don't specify the order of the derivative, the default is 1. So you might just skip that. And then what? You can do a similar thing for f1 with respect to q2. So this is row 1. And then you can go to row number 2, which is just like f2 with respect to q1, and then f2 with respect to q2, right? So let me do that right now for you before we do anything else. So I run it and I just call it test, correct? So if I run that, then you can see the answer here right in the command window, and this is exactly what you expect from your Jacobian. Now also, in addition to doing all of these partial derivatives one by one, there is a command directly in MATLAB that does all of this for you and put it in a matrix form, and the command is called Jacobian. Okay, so this command Jacobian, what you need to pass to it is a vector of the functions, which in this case is going to be f1 and f2, and then the vector of the variables q1 and q2, and that does the exact same thing as the previous line. So let's go ahead and run that, and you clearly can see the results are identical, right? So if you want to write efficiently and use some built-in functions of MATLAB, I would just use this bottom one here. Good. So this is to calculate Jacobian. Now, if you want, as I said, to calculate xi using the same thing, then you add your q1 dot and q2 dot here, right? And then you can also say your xi is equal to what? It is equal to Jacobian times the vector of q1 dot and q2 dot. Okay, and then it multiplies them and gets you the vector xi, which you can see here, definitely, right? This is the end effector x and y velocities. The other thing is, as you know, you can define your q1 and q2 to be functions of time. So you can change them to q1 and q2 of t and add the symbolic variable t. So you introduce q1 and q2 in f1, f2, and then say, hey, can the Jacobian act the same way that we did before and get me the Jacobian? Now, if you look, the answer is no, you are going to get error, because Jacobian expect the second argument to be vector of variables. What you can see, if you look at q1 and q2, they are not symbolic variables, sim, they are sim fun. They are symbolic functions, not symbolic variables. So for that reason, the command Jacobian is not going to work, okay? Now, you might say, well, what if we wanted to calculate xi? If this Jacobian doesn't work, can I say xi, at least take the derivatives of f1 and f2 with respect to time and call it xi? Well, let's try that one. So we say xi is equal to, and you say it is going to be a diff of f1 with respect to t and diff of f2 with respect to t, right? Because f1 and f2 are functions of time now, because q1 and q2 are functions of time. Could you calculate xi for me that way? And you see that it clearly can do it, right? the thing that it has added for you is diff of q1 and t, right? So this is your q1 dot that you define symbolically. Now you have what? You have basically diff of q1 and t, or diff of q2 and t, as you can see. So these are your q1 dot and q2 dot, but definitely you can calculate xi if you want without going through Jacobian. It does, the Jacobian multiplies by q dot vectors and gets you the final answer. So you can do it that way as well. Correct? And then another thing you can do is the command subs, which is an excellent command for substituting a variable with another one. So you say subs in xi, the variable that is called diff of q1 of t and t, correct? This q1 dot that is written this way for you, correct? Change that to what? Change it to the variable q1 dot, correct? So change that derivative with q1 dot. Correct? Then hopefully the new variable that you see, if you again call it xi, it means replace this diff with q1 dot in xi and call it xi again. And then you can do a similar thing here. The next step, again, pass the new xi that you got out of line 15, pass it here in line 16, and say now in the remaining of that, also replace diff of q2 and t with q2 dot. So the final answer that comes out of line 16 ideally should be what? Should be the same xi, but the format that we did it in the past. So let's go ahead and do that. And now you see it is written in a more concise form by replacing these big diffs with just what? q1 dot and q2 dot. So these are excellent commands. Remember what we did in the past, right? We said xi was equal to the j times q1 dot and q2 dot. This is what we did. And now instead we can do it this way. So the result is the same. It's just a matter of how you perform your job. Okay, so let's go back to the original way that we defined these variables. And let's say now somebody gives us some numbers for the length of the members, for the angles of the members, and for the angular velocity of the members. They calculate the xi, the end effector velocities, right? Or twist in this case, the short-term version of twist. So how would you do it if you have a symbolic expression and now you want to replace numbers for symbolic variables? The command to use is called eval. So you say eval xi with all of these numbers that you're going to replace in the xi. Could you give me a number? And if you do that, guess what? You can here. Right? So you see, you can easily get what? You can easily get your values of the end effector velocity, right? So this is one other thing. Sometimes, let's say all you have is just L1 and L2, and you do not have Q1, Q2, Q1 dot, and Q2 dot, just you have the length of the members. When you say eval, it evaluates, but the result is going to be back a symbolic variable because 4 of them are still symbolic, not numbers. Can you do that? Again, the answer is yes, and you're going to get something like this. And it's not too bad. The only thing is the ratios that you will see. And right now, as I said, it's not so horrible because the ratios you see are like 2/5 or 3/5. But when you do these calculations a few times and when these numbers are not nice numbers, right, then the ratios that you will see are gonna look quite uglier. Right, and now you see your ratios are changing, and if you do this several times, then you are going to get even worse. So let me just for the sake of experiment, let me replace some q dot values here and use some not super nice numbers. So now you see you have 48 over 25, 341 over 50, correct? And somebody say, could I have these in decimals instead of these not so convenient ratios? And the answer is yes, but the command to go about it is not eval anymore. Okay, if you want to convert these ratios to decimals, the other command that you have to use, because as I said in I'll show you in the file that I have to do some more calculations, you're going to see some big ratios. The best way to go about it is the command VPA, or variable precision arithmetic. So here you pass to it anything that you want, and you say to convert it to decimals with how many decimals. So let's say here I say, hey, could you eval xi for me with the variables L1, L2, Q1 dot and Q2 dot with whatever I gave you, eval, and if it has these ratios, go ahead and show the result of that with, let's say, 4 decimals, right? This is the number of decimals that you want to show variable precision arithmetic. So convert them to decimals with fractions with, convert them to numbers with decimals with 4 decimals, right? And now look at the difference. You see? Now it converted those numbers that you had into these numbers for you, which are a lot easier to handle than those. Okay. Here, so I wrote the code with some explanations for you, with some comments to make it nicer. There are a couple of other things I want to mention before I go into further tasks of robotics. And one of them is the command simplify, the other one is the command pretty. Although I mentioned all of this in my video on MATLAB Symbolic, but it's a good idea to do some simplifications for you here, and some prettifying, right, of symbolic expressions. So like what? Like many times you might have expressions like, let me show you a simple example. Let's say you also have F3, and this F3 is simply sine of Q1 squared plus cosine of Q1, the whole thing squared, right? If I do that and I say calculate this stuff for me, if you look, it just literally types down for you F3 without trying to say, hey, sine squared plus cosine squared is 1. It doesn't do that, right? So you see clearly it did not do any simplification, but you can use the command simplify, and MATLAB will do its best to make it as simple as possible. So now take a look here. You see, now instead of this expression, it converted to what? To 1 for you, right? So you clearly see the difference, right? This is F3. And then here you can say display simplified F3 is, and then show that result, right? So this might be a little bit better revealing. So simplified F3, the result is what? 1, right? So this is the command simplify, and most of the time it can do a little bit better job too. For example, you might have some term like sine of Q1 times cosine of Q2, and then plus cosine of Q1 times sine of Q2, right? Which is basically sine of Q1 plus Q2. Let's see if MATLAB can do that a little bit better, more advanced tricks, and get your F3 a little bit better, right? So if you do so, you clearly see it converted that into sine of Q1 plus Q2. So absolutely, these are life-saving to get smaller, shorter expressions when you are working with symbolics. If you do not use simplify, and if you do not use eval and especially VPA, you are going to end up with very, very long expressions and with a lot of fractions instead of decimals. So I'm telling you that the command VPA and the command simplify are two lifesavers really when you work with MATLAB Symbolic for robotics, because robotics expressions are typically very long. If you don't simplify and get rid of the fractions into decimals, they're gonna look even scarier looking, right? So another thing you can do is, as I said, the command pretty. And the command pretty typically tries to write it in a nicer format for you. So here, if you look at vector xi, it's not really so bad, right? It looks actually relatively good. And if you apply the command pretty to the xi, I'm not sure if it can do a lot better than what it is, because it is already in a good shape. But let's go ahead and apply that to it. So instead of this one, now it writes it like this for you, which is basically the same. It's just adding these symbols and making it look like bracket. In this case, as I said, it's not gonna look amazingly good, but if you have ratios, it can be really helpful. For example, here I calculated this xi for you, and I want to show you two things. One is xi of 1 over xi of 2, right? Correct? And the other one is the same thing, but just write it pretty. So I want to divide Vx by Vy, or I can say Vy by Vx, let's say, to get the direction of motion really for end effector, right? Or the tangent of angle of that. So if I want to do that, then let's see the difference between lines 15 and 16, right? So let me suppress some of these, and let's go ahead and do it. So look at the difference. One of them is this one, which basically is a long expression, right? And you see the division mark here. The other one, it actually writes it like a division for you by adding all of these dashed lines to be like the division line for you. So you see this is much more readable than this long line. And the longer they are, the more terms you have in denominator and numerator. Typically, this command pretty can make life a lot easier on you. Okay, so that's another thing that I wanted to emphasize for you, the command pretty. Okay, so we have done Jacobian, we have done end effector twist. And now here you can see if I want to do a full calculation for the planar 2 DOF arm forward dynamics problem in the task space or joint space together, then per the two videos that I previously posted, not only we need J, right? We also need, if we go back and look at these formulas that we have, so if we go and look at the formulas for equations of motion, in the Q space, we need three things. What are they? We need the D matrix, we need the C matrix, and we need the G vector, right? So how do we calculate them? Where D comes from basically this expression here. D is basically what? It is mi jvi transpose jvi plus j omega I transpose times ri times ri transpose j omega I, where jvi and j omega I are the two parts of the Jacobian for the centroid of each link. R is the rotation matrix of each link with respect to base, and I is the inertia matrix of each link with respect to the frame passing through the centroid of the link but parallel to frame number I. So can I do all of this basically algebra that we did in one of my previous videos manually? Can I do all of this and get the D matrix basically using symbolic MATLAB? The answer is absolutely. So let me show you how to get the D matrix. So here, these are the inertia matrices for the two links with respect to the frames passing through their centers, as we did in one of my previous videos, right? I1 and I2 here, these numbers I1 and I2 I already calculated, so they are numbers. So here, the length of the link, the mass of the link, the location of the centroids, the moments of inertia, and the g for gravity, they are all given as numbers, okay? But the joint variables, the joint velocities, and the end effector velocities are given as symbolic. So what you can see here, I have defined JV1 the same way that we define it in the previous video that I have. If you look, if you go back here, right, we had, let's find it, JV1. So it's negative A1 S1 over 2, 0, A1 C1 over 2, 0, 0, 0. That's JV1, and that's exactly what I typed for you here. Then we have JV2, which again, that's this matrix here. So I have typed it in for you. Then we have J omega 1 and J omega 2, which again, we calculated. So let me show you those here. That's J omega 1 and J omega 2. We also have the rotation matrices for each link, right? Which again, you see I have typed them in. And we also have, as I said, the inertia matrix for each one of the links. And once I have all of these components, I just follow that formula I showed you for the D matrix. This is a summation over the number of links. I have 2 links here for this 2 degree of freedom planar arm. And all I need is that summation goes from 1 to 2, right? And this is exactly what you see I have done here. So this is the translational term for the first link. This is the rotational term for the first link, and the same thing for second link. And when you add them together, then you see before I show the D, which is going to be a quite big thing, I first simplify it, and then I convert all of the fractions in it into what? Decimals with 4 places of decimal, and then call it D. Otherwise, they are not going to look amazingly nice here. So just to show you the effect, I'm going to stop the code here, and I'm going to show you both versions. One is this one, the output of line 48 basically, which is the D in its raw format without any cleaning basically, and making it nicer and simplified. The other one is at the end of line 54.5, which shows the after simplification, right? So let's go ahead and run this for you here. So this is D, this big thing that you can see here. Just look how big it is. This is the D matrix if you don't do any simplification and VPA. Look at that. You see how big it is, right? It's just this big. And you have some big fractions, as I told you, right? Like what? Like, for example, I have numbers like something 9 divided by 250, and as you go forward, they get even worse. Now you have 30 over 9370 and 9375, 9 over 12,500, and you see you get some big nasty fractions. But if I simplify and if I do VPA, this is the result. Look how nice it looks like, right? Extremely nice. Because now it goes ahead and simplifies these two and say, hey, this is cosine squared plus sine squared. And then both of them over 100. So the result is just 1 over 100 here. And then it tries to do some further simplifications. And then this is what you ultimately get. So my recommendation is absolutely use those 2 commands, right? Simplify and VPA on any big matrix that you get in your calculation. So this is your D matrix, the inertia matrix for this robot. The next thing we calculated for this was the Christoffel symbols and the C matrix, right? So your next step is now to get the partial derivatives of components of D with respect to the Q's, and define what? The Christoffel symbols of first kind Cij, and then put these Cijks into a matrix and call it what? C of Q and Q dot, right? So that's what you see I have done here for you. I used the command diff. I calculated the partial derivatives of the components of D, which I acquired here, just like any regular matrix. I got those components from the D matrix, D11, 1, 2, 2, 1, and 2, 2. I calculated, I just assigned them to these variables, and then you see the formula for Cijk, I exactly copied and pasted here. Calculated all of the 8 C's that I have, and then based on the previous video, if you watched it, I put those C's combined with the Q dots, and I format my C matrix. Again, before I show my C matrix, I did a what? I did a simplification and then VPA with 4 decimals. So now this is what I do this time. I'm gonna run the code all the way to line 70, and let me suppress this D. I don't need to see that big D anymore. So let's go ahead and run. And now you see this is your D matrix. This is your Jacobian. This is Jacobian dots, by the way. We'll talk about it in a second. Let's see, for some reason it did not show C, I guess. Oh, I forgot to remove that. But let's do it again. So now you should have C matrix, and this is your C matrix, right? It involves Q's and it involves Q dots. So it's a C of Q and Q dot. But D is only a function of Q, so that's just D of Q. Right? So you see I easily calculated C and D just using the diff command. I calculated my Jacobian also using the diff command. As I told you, I could have calculated this J simply by what? By using the command Jacobian, right? So I could say this is Jacobian of vector f1 and f2 with respect to the vector q1 and q2, and that would do the exact same thing. Now, where do I need this J dot? As I said, I need it when I want to find the equations of motion in task space. If you remember, when we found the equations in the task space, one of the components that you need here for the eta function is J dot time derivative of J. And that's what I did here in the code. When I calculated J, then I said J dot is basically the differential of the components of J, and then multiplied by the Q dots, right? Or if I define my Q's to be functions of time, then I could use, say, diff of J with respect to T, right? So that's what I have here. So here you can see that J dot, J, D, and C. What else do I need to calculate? If I go back to the, again, Q space, I need vector G, and vector G, the components of it are the partial of the potential energy with respect to the components in Q. So what I need to calculate is the potential energy of this robot, and it's no big deal. It's just summation of individual potential energies, and that's the formula for individual potential energies, right? The G of gravity times the position vector of the centroid of each link, measure the height of it. This is really the if you write G as a vector here, like 0, negative 1, 0, or 0, negative G, 0, and then this R, this transpose times R, basically it will translate literally, this whole thing will literally translate to G times Y of the centroid, right? Because G, as I said, is a vector. This G is going to be like 0, negative G, and 0, or if the Z is the upward direction, right? It depends on what, in our case, the upward direction is Y. So it's going to be like this, and if your R of Ci is like X of Ci, Y of Ci, and Z of Ci, when I do G transpose times R, it's like the dot product, you only get these two, right? And you might say, well, where did the negative go? You have to change that in the G because this is for the case of potential energy. And if your point is, it now depends on where your point is. If your point has a positive Y, and when I say positive, with respect to what? With respect to datum, and here the datum could be your XZ plane, really. Then it's going to be positive. If it's below that, it's going to be negative. So what you need is really to change this to positive G. So this G transpose R is translated literally to GY. And that's exactly what I did here in the code. I directly did that product right here. So this is the Y of centroid 1, and this is Y of centroid 2. And then I found G1 and G2 through partial derivatives of potential energy with Q1 and Q2, and then formed them into a vector. Again, I simplified, used VPA. And so now you clearly see my G vector is all good to go, right? So now if I want to write my equation of motion in the Q space, I'm done because I have my D matrix, I have my C matrix, and I have my G vector. So writing the equation of motion in the jointed space is over. That's all I needed. These three. I'm done. If I want to write it in task space, I need a few other things. One of them is J dot, which we already calculated. The other one is the big lambda, right? And if you remember, the formula for big lambda was what? It was J transpose inverse D times J inverse. And that's what you see I have done here in the next line. Inverse of J transpose, right, times D times inverse of J. I simplified it. I don't need to do simplification twice here. It seems like I did it twice. You simplify it again, use VPA, and then you show the lambda. Now pay attention here, one specific thing, and that's the command transpose. If you want to transpose a matrix, a symbolic matrix, do not use the quotation mark. Okay, that's not really, most of the time is doing this job. So here you see I have J. If I say J transpose, you see, it does give me something crazy looking. Look at this. All I needed was to just transpose this matrix. And I use quotation, but it gave me something very weird. So if you ever want to transpose, inverse is okay, but transposing a symbolic matrix, you have to use the command transpose, not using a quotation. So if I say transpose, right, now you see it is definitely doing a lot better. It doesn't have this conj, right, the conjugate. It is showing a lot better, except it has all of these big decimals, and if you want you can limit that. You say, hey, show the result of that, but maybe with 3 decimals, not with I don't know how many decimals is that, right? And that makes it look a lot nicer like this. Okay, so if you want, you can, when you do your transpose, right, of a symbolic matrix, if you want, you can immediately also apply your VPA on it, or if you don't do it immediately, then when you do the simplification of everything, make sure you do a VPA, so you don't have those huge amount of decimals. If you do it later, it reduces the chance for a round of errors. Okay, so you better do all of your calculations, and then at the end do the truncating the decimals, instead of for each one of these do it and then multiply, because it's going to be cumulative effect. That's what I did. I did the regular transpose. As I said, I did not use quotation, and then I did the simplification at the end. And now if you look here, I'm going to run it for you. Now I can get my lambda matrix, which is only a function of q's. This is my lambda. Clearly now it is looking bigger, right? Now definitely it is going to look a little bit bigger, right? Lambda is by no means as simple as D and C, because now you have combinations of Q1 and Q2 in it. And as you can see, you have some big numbers here too. And although I use VPA, it did not do an amazing job. So I have e to the power 63, and you might say, well, that's like literally infinite. It is, but they are also divided by some other huge numbers, right? When you see they're divided, now they are divided by some big numbers like this. Okay, so lambda is not going to be as beautiful looking, and worse than that is eta. If you remember, the eta matrix is like a modified version of C and G, and there was J dot in it and Xi in it and everything. So if you remember, this was the formula for eta, right? You see there are tons of terms in it, and there is some substitutions to be done. I mean, wherever you had Q dots, right, in your matrix C, it was C of Q and Q dot, and then it was also multiplied by Q dot. So anywhere in your governing equation, if you had Q dot, you have to now replace it by what? By J inverse times Xi. So not only you have to define Xi as a symbolic variable vector of Vx and Vy, which we did already in the top of the code, right? And then we define Xi here. So wherever I see Q dot, as I said, I have to replace it with what? With this J inverse times Xi, and that's what you see I have done here. So first I multiplied inverse of J by Xi, simplified it, did a VPA on it to make it a little bit look nicer. So this temp variable for me is J inverse times Xi. And now wherever in the C matrix I have Q1 dot, I'm going to replace it by the first component of this J inverse times Xi. Wherever I have Q2 dot, I'm going to replace it by second component of this temp vector. The same thing is in J dot. If you look at your J dot, right, your J dot definitely has in it, again, Q1 dot and Q2 dot. So I have to do that replacement as well here. And this temp variable also, as I said, needs to be multiplied by the C matrix as well. So if you look at the formula here, it's inverse of J transpose times C substituted, right? In C, I substituted Q dot for J inverse Xi, so I call it C sub. I added G to it, so basically it's this part inside the parentheses, multiplied by J transpose inverse, minus lambda times J dot, where J dot, again, in it, there is a substitution, and that's what I did here. I call it J dot sub, so you see, minus lambda J dot sub times temp, and that temp is this guy here, J inverse times Xi. Okay, so that's the formula for eta, which I have applied here. And at the end, I also simplified it. I also did a VPA on it. And with all that you do, when you do it, first of all, it takes MATLAB some good time to calculate it. If you see here, I have jj.dcg lambda, but it is still working on eta to simplify and to get rid of some of those big numbers, big fractions. Still, you see, it takes some good time out of MATLAB, and when it does, the size of eta is going to be much, much bigger than your D, C, and everything else, right? So if you look at the relative sizes, J is the same size as D, C, and G. J dot is a little bit bigger. Your lambda is quite bigger. And then when eta comes in, lambda is going to be like a tiny thing compared to eta. Okay, so of course, if you know the numbers, you can always use the command evals, right? If you know your Q1, Q2, or the dots or V's, you can easily use the command eval, and those huge formulas are going to just convert into a bunch of numbers for you. But since I'm doing everything pure symbolic here, this is basically what you'll get at the end of the day. So you see, still working on it. There we go. Now finally got eta, and now look at the size of eta. Look, when lambda is finished, it's here. Lambda is done. Now look, eta is going to keep going. You see? That's how big eta is compared to lambda starts here, and then after you go a lot, then finally C and D show up. Okay, so it is a lot of algebra to be done. And if you remember when we did it all by hand too, the equations were not so beautiful looking. Even in the joint space, the equations were relatively big, but now when you go to the task space, just the lambda itself, if you looked at it, it was this big of a thing. And I did not even bother when I did it manually to go for eta, because it's just a lot of algebra. So here I use MATLAB to do the algebra for me, but you clearly see how big eta is. Good enough? So hopefully this video was useful to you, and you can use the symbolic tools to perform kinematics, kinetics, and later when we get to control of robotic manipulators, mobile robots, and anything in this regard symbolically. Because symbolic gives you the advantage of doing those differentiations, right? Jacobians and so on, and doing the algebra basically for you. So thank you so much for your attention. I'll see you in my next video.